In the last class, I introduced this idea of a proper cone. Right? It's a special kind of a cone which is convex, closed, solid, and pointed. If it satisfies all of these four properties, it's called a proper cone. And we saw a few examples. We saw that, for example, the non-negative orthant was sort of the first classical example of a proper cone. And similarly, you also have, let's say, the subspace, which is not a proper cone because it's not pointed. And we also saw that let's say the second order cone is a pointed cone. The ice cream cone is a pointed cone. And another special class of proper cones is this class of positive semi-definite matrices. In the previous class, we showed that it's a convex cone, it is closed and it is pointed, but I didn't give a complete proof for the property that it is also a solid cone. So let's try to prove that. Of course, I showed how you could show it for let's say 2 by 2 positive semi-definite matrices, but instead of taking just the special case, I mean, this all it amounts to is just algebra in order to prove that a 2 by 2 positive semi-definite matrices forms a proper cone. But we can, without much difficulty, we can also prove that general n by n positive semi-definite matrices, these are solid. And when I say solid, again, it's in the space of symmetric matrices. That's the underlying vector space that we're thinking of. And this vector space has dimension n into n plus 1 by 2. Right? And recall that in this context, in this particular space, the inner product between two vectors or two matrices in this case is essentially the trace of A transpose B. All right, and the ball that we consider is not it's not the standard Euclidean ball, but instead it is the set of all symmetric matrices for which whatever the two norm of this Frobenius norm of the difference between x and a, the mean in this particular case, or the center, is less than or equal to epsilon. Right? So the square root of the trace of x minus a transpose x minus a, that is less than or equal to epsilon. Okay. So our goal is to, of course, show that this cone is solid. And just to recall us, what is a solid cone? A cone is said to be solid if essentially it has a non-empty interior, right? So again, a few of you had questions about what exactly constitutes a solid cone. So let's clear up all of those misconceptions right now. So what is the difference between a solid set and an open set? Yeah. So in general, so what's the connection between a solid set and an open set? So every open set is solid, right? And why is that the case? By definition, an open set should contain a ball. In fact, for every point in the open set, I should be able to construct a ball of some radius epsilon around it, which is fully contained in S, in the set, right? So, which means that every open set is solid. So, one example of an open set in Rn is, let's say, the open ball. Such that the 2 norm of x is, let's say, strictly less than 1. This is an example of an open set, and it is obviously solid. Now, what about the following set? Xn in Rn such that the norm of x is less than or equal to 1. What kind of a set is this? It's a closed set, but is it solid? It is solid, right? So this is an example of a solid set which is not open. But a property of a solid set is that every solid set always contains an open set. There is it's possible to construct some subset of the solid set which is open. Okay. So one example of, let's say in R3, an example of a proper cone was basically the ice cream cone. Right. So this basically is the boundary of the ice cream cone. Everything sort of in this interior is included as part of the cone, so it's solid. Right? It's possible to draw, so take any point inside in the interior of this particular proper cone, inside the ice cream cone. It's possible, you can see geometrically that it's possible to place a ball inside this particular cone. Right? Now on the other hand, let's look at another cone which is also pointed, which is effectively of this form. Essentially, I take a paper cutout, right? It's basically a cone in R2, but then I keep this in R3. So on a paper sheet inside R3, right? This is a cone, correct? But it is not solid. It's not possible. No matter which point you take on this particular sheet, you can't really place a ball inside it. Yes. Because you're considering R3. Yes, that's why. Whenever we are making all of these statements, you should always, the first question to ask is, what is the underlying space? What is the underlying metric space? And in this case, it is R3. Okay. So in R3, this is not a proper cone. But on the other hand, if my space was R2, then this could potentially correspond to a proper cone. All right. But what is to be kept in mind is this has an empty interior, because interior is always an open set in Rn, in this case R3, so it should be solid. But this has a non-trivial relative interior, right? Because relative interior, for the relative interior, the underlying space is the what is the underlying space for the relative interior? R2, but in general, correct. So it's basically an open set within the affine hull, right? So the underlying space would be the affine hull. But when we say in general the interior, it's not the affine hull, but rather the entire space, R3 in this case. Okay. So that's what we mean by a solid cone, and our goal is to show that the set of positive semi-definite matrices forms a solid cone. So it has a non-empty interior, and we make an even stronger statement. So the set of positive definite matrices is basically the interior of the set of positive semi-definite matrices. Okay, we can exactly characterize the interior of the set of positive semi-definite matrices. So how do we show something like this? Right? What we want to show, let's first start out by understanding what we want to show. The first point that we have to show is that every positive definite matrix corresponds to an interior point of the set of positive semi-definite matrices. So effectively what we want to show is if A is a positive definite matrix, then we need to show basically what we want to show is that there exists some epsilon greater than 0. This epsilon could depend on A. Okay, so we want to show that there exists some epsilon greater than 0 such that for all symmetric matrices, let's call it E, n by n symmetric matrices E, you can think of this as the perturbation around A. Okay, so for all n by n symmetric matrices E with the norm less than epsilon, let's say with, so what is the norm in this case? Let's explicitly write that out, with trace of E transpose E less than epsilon square, right? Because the norm is the square root of the trace of epsilon of E transpose E. So as long as the trace of E transpose E is less than or equal to epsilon square, A plus E also belongs to the set of positive. So basically A plus E is also a positive semi-definite matrix. Okay, so loosely speaking, again, this is not the exact geometric picture, but just to sort of understand, we have the space of symmetric matrices, right? The space of all n by n symmetric matrices, and in this case, what I want to understand, what is the relationship between the set of positive semi-definite matrices and the set of positive definite matrices, right? So within this, I have the set of positive semi-definite matrices, which I claim forms, which we know is a cone, all right? And inside this somewhere we have the set of positive definite matrices. So suppose I pick some positive definite matrix. Okay, so this would be our matrix A. Again, this is not the correct geometric picture because we can't really interpret it, but let's try to at least get some intuitive understanding of what we want to show. So around this, I look at A plus E, right? So this vector here, suppose that this is E, this is some vector. The vector addition of A and E. So this gives me another point. This is my A plus E. Okay, so E is some perturbation of A, and the resultant is A plus E. Correct? So no matter which A plus E I take, so as long as it is within a certain distance of A, as long as it's not too far away from A plus E will always be a positive semi-definite matrix. Right? That is what we want to show. Okay, is that clear? Great. So in doing so, what can we use? What properties of positive semi-definite matrices can we use? Okay, why is that? Okay.
Reduce that to some diagonal matrix. The product should remain positive.
Okay, but okay, what properties do we know about positive definite matrices? Yep, x transpose Ax should be greater than or equal to 0 for all vectors x. That's number one. What is the other property that we know? All the eigenvalues are greater than or equal to 0. What else do we know about symmetric positive semi-definite matrices? Yeah? The eigenvalues are real, they're greater than or equal to 0 for positive semi-definite matrices. But what other property have we studied about positive or in general symmetric matrices? Correct. So we have orthonormal we can it is orthogonally diagonalizable, so we can construct a basis of orthonormal eigenvectors. Okay. So let's try to use that in order to prove this particular statement. We want to show, let's say we want to show this particular statement. So suppose that I start with a positive definite matrix A. What do I know? I know that all the eigenvalues of A are strictly greater than 0. Okay. So let us say that lambda 1, lambda 2 up to lambda n are the eigenvalues of this particular matrix A, and suppose that V1, V2 up to Vn are the corresponding orthonormal eigenvectors. Okay, and let me also assume that lambda min is the minimum eigenvalue of A. So lambda min is the minimum over all I of lambda. It's the smallest eigenvalue. Okay. Now suppose I need to choose a particular epsilon, right? This epsilon is allowed to depend on A. Let me say that I choose epsilon to be anything less than lambda min. Okay, any value less than lambda min. So choose epsilon which is less than lambda min. Maybe it's lambda min by 2. Okay, I know that lambda min is strictly greater than 0 because it's a positive definite matrix. Okay, so I fix any arbitrary epsilon less than lambda min and say that matrix E is symmetric and the trace of E transpose E is equal to epsilon or anything less than or equal to epsilon. Okay, but what is E is a symmetric matrix, so what is E transpose E? Yeah, it's just E square, right? So it's a trace of E square is less than or equal to epsilon. Okay, sorry, I'm sorry, this should be less than or equal to epsilon square. So trace of epsilon E square is less than or equal to epsilon square. So what can you say about the eigenvalues of E? So suppose that, let's say, assume that row 1, row 2 up to row n are the eigenvalues of the matrix E. What are the eigenvalues of E square? Yeah, it will be row 1 square, row 2 square, row 3 square up to row n square. Okay, and so row 1 square, row 2 square, row n square are the eigenvalues of E square. So what can I say about the eigenvalues of E in terms of epsilon? Correct. So effectively what I have is summation I equal to 1 to n rho I square is less than or equal to epsilon square. So I can say that any rho I should be less than or equal to epsilon. Okay, that's what I need. Or the absolute value of rho I is less than or equal to epsilon. Okay, great. Now, so remember that E is an arbitrary symmetric matrix. So the rho i's need not be positive; they could be negative. Okay, but what I have here is a bound on the absolute value of each eigenvalue. The eigenvalues could be negative, but they can't go too negative. That's the point that I want to make, because E has sufficiently small norm. We don't want the norm to be too large. Okay. So I'm taking A, I'm perturbing it by E, and I want to ensure that I want to show that the resultant is still positive semi-definite. Okay. So what can I say about eigenvalues of any general symmetric matrix? Right? I need some bound on the eigen. So if I'm able to show that the minimum value or the minimum eigenvalue of the matrix A plus E is strictly greater than 0, then I'm done. Correct? Because I want to show that lambda min, so I basically want to show that A plus E is positive semi-definite. In fact, I'll show that it is positive definite. Okay. Now I need some bound on the minimum eigenvalue of A plus E. I have bounds on the eigenvalues of A and E separately. Right? I know that the minimum eigenvalue of A is lambda min. Okay, the largest eigenvalue could be whatever, I don't care. And the minimum eigenvalue, what is the minimum eigenvalue of E? Huh? Correct, minus epsilon, right? It's something which is at least minus epsilon. So if I'm able to show that lambda min of A plus E is strictly greater than 0, I know that lambda min of A is strictly larger than epsilon. Okay. So what do you know about the eigenvalues of the sum of two matrices? Yeah. Okay, and why is that the case?
Right, A, B is equal to lambda,
Okay.
where B is less than or A plus.
Okay. Again, remember that A and E need not have the same set of eigenvectors. Right? The eigenvectors of A could be different from the eigenvectors of E. Right? In general, they will be different. All right. So let me assume that let's say U1, U2 up to UN are the eigenvectors of the matrix E, and these correspond to the eigenvalues rho 1, rho 2 up to rho n. Okay, so V1 through Vn are eigenvectors of A, and U1 through Un are eigenvectors of E. Okay, now if I give you any general vector, right? So let's suppose that so I have A plus E, right? Let me say that the matrix C is equal to A plus E. What I know for sure is that C is a symmetric matrix because both A and E are symmetric matrices. All right. Now, how do I get some bound on the eigenvectors of C? Okay. Let's suppose that W1 through Wn are eigenvectors of C, and I need something else. Mu1 through Mun are the corresponding eigenvalues. Right? we've already seen this before, but you know that any vector x can be expressed, because w1 through wn are eigenvectors, they're orthonormal eigenvectors. You can write any x as a linear combination of w1 through wn. You can also write it as a linear combination of u1 through un and v1 through vn, because they're all different sets of eigenvectors, so they correspond to different bases for Rn. So I can write x as, let's say, summation I equal to 1 to n alpha I vi, but I can also write it as summation I equal to 1 to n some beta I ui, and also this is summation I equal to 1 to n some gamma I wi. Okay. Now suppose you wanted to find the largest or the smallest eigenvalue of a particular symmetric matrix, how would you get it? Correct. So x transpose ax. So I can look at the maximum of x transpose ax, and that would give me the largest eigenvalue, right? We're going to use something similar, right? So if I take any x transpose, let's say cx, what is this equal to? I can express x trans x as in terms of, let's say, these eigenvectors, right? Eigenvalues and eigenvectors. So it is summation I equal to 1 to n gamma I wi transpose c times summation I equal to 1 to n gamma I wi, right? Which is nothing but summation I equal to 1 to n gamma I gamma j wi transpose c wj. But what is c times wj? Correct. So it is mu j times wj. So this is nothing but summation I equal to 1 to n gamma I gamma j mu j wi transpose wj. What is wi transpose wj? What kind of eigenvectors are w1 through wn? They're orthonormal, right? So wi transpose wj would be equal to 0 if I is not equal to j, and it is equal to 1 if I equal to j. So this just gives me summation I equal to 1 to n gamma I gamma j mu j, that's it, right? Or in other words, so this is I equal to j, so it is just gamma I square mu j. Okay. So in general, if you have a symmetric matrix C, any x transpose Cx is basically equal to summation I equal to 1 to n gamma I square. So x is represented in terms of these gamma i's, gamma I square times mu j, the corresponding eigenvalues, right? So it is the square of the coefficient of the eigenvector times the corresponding eigenvalue. That is what you will get. Okay. So far it's fine. Great. So similarly, okay. So maybe I should have been more careful. This is summation j equal to 1 to n gamma j w. I'm using the same index, but actually these are two different sums, right? So So this is perhaps this is better notation. So this double summation is basically coming from n summation j equal to 1 to n. So one summation is coming from these terms, the other summation is coming from these terms. Okay, so this is x transpose cx. Now what can I say about x transpose ax in terms of the eigenvalues and eigenvectors of A? So I know that x is equal to summation alpha I vi, right? I have this over here. These are the eigenvectors of A. So this would just be summation I equal to 1 to n alpha I square times lambda I, because lambda i's are the eigenvalues of A. And similarly, x transpose ex, what can you say about this? So beta 1 through beta n are the coefficients of the ui's in terms of and rho 1 through rho n are the eigenvalues of. So what would this be? Beta I square times rho I. It's not rho I square, right? Okay, but what is C? It is equal to A plus E, right? So x transpose Cx, let me write this in a separate page. So x transpose Cx is equal to summation gamma I square times mu j but it is also equal to x transpose Ax plus x transpose Ex. So summation I equal to 1 to n alpha I square lambda I plus beta I square rho I. Okay. What I want to understand is, okay, so now if I had to get the smallest eigenvalue of, so these are, so mu 1 through mu n are the eigenvalues of A plus E. A plus E. These are the eigenvalues of A, and these are the eigenvalues of E, right? And let's also assume that the norm of x equal to 1. Then what can you say about the gamma I squares? So remember that x is equal to summation alpha I vi, summation beta I ui, and summation gamma I wi, where all these vi's and ui's and wi's, they are sets of, they are orthonormal bases. They're orthonormal, right? So what is the norm of x in terms of these coefficients? Correct. So the 2 norm square of x would be equal to summation alpha I square. That would also be equal to summation beta I square, which is equal to summation gamma I square. Okay. Again, all of this we're just representing things in terms of the eigenvalues and eigenvectors of A, E, and A plus E. Great. So now suppose we actually chose x to be, let's say, the eigenvalue, the eigenvector corresponding to the minimum eigenvalue of A plus E. Okay, then what would this be equal to? Or okay, let me put it in a slightly, let me get something even more general. So what I know is that summation I equal to 1 to n gamma I square is equal to mu j. Sorry, this is equal to 1. Correct? So in other words, the gamma I squares are all non-negative, no matter what the gamma i's are, and they sum to 1. So basically, this is just a convex combination. Right? So this is a convex combination. So this is basically just a convex combination of the mu j's. Okay. And what can I say about how large or small this can be equal to? These are also convex combinations of lambda i's and rho i's. So now what can I say about mu min with respect to lambda min, rho min, or lambda max, rho max? Mhm.
That sum, so if gamma is 1 by root n,
If gamma I is 1 by root n, okay,
that is the case, gamma is
summation gamma I is max, okay, but I'm not interested in that, right? So I'm interested in the maximum overall j of mu j. Remember, that is what I want.
we need to somehow bound each
Mu I.
coefficient term.
Because we want to basically bound each mu I, right? Because mu j's are the eigenvalues of A plus E. What I want to show is, what I want to know is how large can the eigenvalues of A plus E be, how small can the eigenvalues of A plus E be, in terms of the eigenvalues of A and E. Okay, so let us just first try to bound this particular quantity. Okay, I know that summation I equal to 1 to n gamma I square mu I, sorry, this should have been mu I, this is greater than or equal to summation I equal to 1 to n alpha I square lambda min plus beta I square rho min. Do you agree with that? Because each lambda I is greater than or equal to lambda min, and each rho I is greater than or equal to rho min. That's it. Okay? Because this is exact, right? So lambda I is greater than or equal to lambda min, rho I is greater than or equal to rho min. So I just use that particular property. This is equal to summation I equal to 1 to n alpha I square plus, or let's say alpha I square times lambda min plus summation I equal to 1 to n beta I square times rho min. But what do I know about lambda min and rho min? Sorry, what do I know about summation alpha I square and summation beta I square? They're both equal to 1. So this is just equal to lambda min plus rho min. And this is true for every convex combination of mu I. Right? For every set of gamma 1, gamma 2 up to gamma n, such that the sum of the squares is equal to 1. This is greater than or equal to lambda min plus rho min. So what can you say about the minimum of all the mu i's? that should also be greater than or equal to lambda min plus rho min, right? So mu min can be obtained by choosing some particular combination of gamma 1 through gamma n, right? This is true for all gamma 1 through gamma n, and this by choosing one particular gamma through 1 through gamma n, basically they'll all be 0 except a 1, where you put 1 corresponding to mu min and 0 for all the other mu's. Okay, so which means that mu min is greater than or equal to lambda min plus rho. So the minimum eigenvalue of a sum, at least for symmetric matrices, is always greater than or equal to the sum of the minimum eigenvalues of the two corresponding matrices. Using the same argument, you get that mu max is less than or equal to lambda max plus rho max. Okay, this is true for any symmetric matrix. Okay, so what we've now shown is that given any symmetric matrices A and E, the minimum eigenvalue of the sum is greater than or equal to the sum of the minimum eigenvalues. But now from our choice, what can we say about lambda min plus rho min? It is strictly greater than 0, because the minimum eigenvalue of E is at most epsilon, and the max and the minimum eigenvalue of A is strictly greater than epsilon. So E and epsilon minimum eigenvalue of E, which is rho min, this is, so this is at least minus epsilon, right? The absolute value of rho min was at most epsilon, so rho min should be greater than or equal to minus epsilon, and the minimum eigenvalue of A, which was lambda min, is strictly greater than epsilon. So mu min, which is the minimum eigenvalue of A plus E, is strictly greater than epsilon minus epsilon, which is 0. So even though some of the eigenvalues of E could be less than 0, but they can't be too negative, what we have shown is that the minimum eigenvalue of A plus E is going to be strictly greater than 0. Right? So A plus E is positive semi-definite. Okay, so just to maybe quickly recap, there were two things. One, we showed that given any symmetric matrices A and E, the minimum eigenvalue of the sum of A and E, so minimum eigenvalue of A plus E, is greater than or equal to the minimum eigenvalue of A plus the minimum eigenvalue of E. Since we know that A is positive definite, we chose this particular epsilon such that it is strictly less than the minimum eigenvalue of A. It is less than lambda min. Okay, but as a consequence of this particular epsilon, all the eigenvalues of E are guaranteed to lie between minus epsilon and plus epsilon. Okay, that's how we've chosen this perturbation E. And using this particular property of the sum of symmetric matrices, the minimum eigenvalue of A plus E therefore has to be strictly greater than 0, because the minimum eigenvalue of E is at least minus epsilon, and the minimum eigenvalue of A is at least epsilon. So the sum has to be at least 0. Right? So coming back to this particular picture, of course these were in terms of, we thought of these, at least we imagined these to be something like Euclidean balls, but in fact we were interpreting everything in terms of the eigenvalues. Okay, just from the Frobenius norm, we were trying to use that to get bounds on the eigenvalues of A and E. Right? Any questions? So right now all we've shown is that every positive definite matrix is an interior point of the set of positive semi-definite matrices. We haven't shown that there are no other interior points. Okay? So I leave that as an exercise for you to show that if a matrix is not positive semi-definite, then that cannot be an interior point. So what should happen if a matrix is positive semi-definite but not positive definite? Yeah, it should lie on the boundary, but what can you say about, let's say, the eigenvalues of the matrix? There should be at least one eigenvalue which is 0. Okay, all of them should be greater than or equal to 0, but at least one of them should be equal to 0. So in this case, I leave it to you that you can find some E such that no matter how small you make epsilon, you will always be able to go outside the set of positive semi-definite matrices. Okay. Yes.
So could you discuss the last step? Where we proved that mu min is greater than lambda min?
Correct. You proved that this is the case. Okay. So you agree that this is greater than or equal to lambda min plus rho min. There is no problem with that, right? And this is true for every gamma 1, gamma 2 up to gamma n, right? So suppose that mu1 is greater than or equal to mu2, greater than or equal to mu3, and so on. I've ordered the eigenvalues. Okay. Now this statement is true for all gamma 1 through gamma n. Correct? For all gamma 1 through gamma n, this quantity is greater than or equal to lambda min plus rho min. So let me choose a specific gamma 1 through gamma n, where gamma 1 equal to 0, gamma 2 equal to 0, all are equal to 0 except gamma n, which is equal to 1. Okay, so just to write that out. So we know that summation I equal to 1 to n, gamma I square mu I is greater than or equal to lambda min plus rho min. This is true for all gamma 1 through gamma n, such that summation over Ri gamma I square equal to 1, because the 2 norm of x has to be equal to 1, right? That was the fundamental assumption. So this holds true for all of these. Now if mu1 is greater than or equal to mu2 and so on is greater than or equal to mu n, then you just choose gamma 1 equal to 0 equal to gamma 2 up to gamma n minus 1. The first n minus 1 you set them equal to 0, and gamma n you set equal to 1. Now even for this choice of gamma, this should be greater than or equal to lambda min plus rho min, right? So, but what is the left hand side equal to? It is just mu n greater than or equal to lambda min plus rho min. But what is mu n? That's just mu min. Alright, that's it.
So in both of these mod x, norm of x square is equal to 1.
Correct.
So why?
I mean, if not, I mean, it doesn't have to be the case. Basically, summation alpha I square would be equal to the 2 norm of x the whole square. This would be 2 norm of x the whole square. I just have to do another normalization step. That's it. Just to avoid that, I assume that 2 norm of x equal to 1. Otherwise, I'd get a 2 norm of x on the left side and 2 norm of x on the right side, and those would basically just cancel. This just makes it convenient. Any other questions? Yeah.
But a plus c is PhD.
Correct.
But what it specifically PhD is.
Correct. It's positive definite. Yes.
So in a way, they're just using the fact that it's anyway PhD, so you're right.
Correct. That's it. It's in fact positive definite. But it suffices to just show that it is positive semi-definite. So we know we've proved that for all I, the absolute value of rho I is less than or equal to epsilon, right? Because we showed that summation rho I square is less than or equal to epsilon square, correct? So each rho I square should be less than or equal to epsilon square, or the absolute value of rho I should be less than or equal to epsilon, which means that rho I can be at most epsilon and has to be at least minus epsilon. That's it. Any other questions? Okay, yeah, so the exercise, show that if A is positive semi-definite but not positive definite, then A is not an interior point of the set of PSD matrices. Okay, because we've shown that every positive definite matrix is an interior point, but we've not really shown that matrices which are not positive definite are not interior points. But this is, again, use a very similar approach. You will see that at one point something breaks down. Okay, now what was our motivation for studying proper cones? It was to define these so-called generalized inequalities. And one example of a generalized inequality, as we saw, was component-wise inequality for vectors. So you take any two vectors in Rn, we say that vector 1 is less than or equal to vector 2 if every component of vector 1 is less than or equal to every component of vector 2. Okay, so obviously not every two vectors are comparable, but you can definitely compare some set of vectors. So we defined, so if K is a proper cone, then we define the corresponding generalized inequality as follows. So we say that vector x is less than or equal to vector y under the generalized inequality corresponding to the proper cone K if y minus x belongs to the proper cone. Okay, and if we go back to our example of the component-wise inequality, the corresponding proper cone was just the non-negative orthant, right? So x is less than or equal to y component-wise if and only if y minus x belongs to the non-negative orthant. And that's easy to see because it means that every component of y minus x should be greater than or equal to 0. Okay. Now, Now, why do I call it a generalized inequality? What properties should generalized inequalities satisfy? So firstly, what properties do inequalities satisfy? Okay, so suppose I have some operation, right? What is an inequality? It's an operation on pairs of elements, right? So we say that it's an inequality that induces a partial order if the following properties are satisfied. It is reflexive, which means that x is less than or equal to x for all x in the set. Okay. The second, it should be anti-symmetric, which means that x is less than or equal to y and y is less than or equal to x. If this happens, if x is less than or equal to y and y is less than or equal to x, then should be the case that y should be equal to x. And the third, it should be transitive. Which means that x is less than or equal to y and y is less than or equal to z should imply that x is less than or equal to z. Before seeing what constitutes inequalities that induce partial orders, let's see an example of something which does not give you a partial order. Okay, so consider, let's say, an inequality on pairs. So x1, x2. I'll say that this is less than or equal to y1, y2 if x1 is less than or equal to y1. Okay, so given two vectors x and y, I'll say that vector x is less than or equal to vector y if the first component of vector x is less than or equal to the first component of vector y. All right, is this reflexive? Yes, right, because x1 is less than or equal to x1 anyway. Is it transitive? If x is less than or equal to y and y is less than or equal to z, then it must mean that x1 is less than or equal to y1 and y1 is less than or equal to z1. So x1 is less than or equal to z1, or x is less than or equal to z. So it is transitive, but is it anti-symmetric? Is it? So suppose I have 1, 2 and 1, 3, right? If this is x and this is y, x is less than or equal to y, but y is also less than or equal to x. But that can happen without x being equal to y. Correct? So it is reflexive, it is transitive, but it is not anti-symmetric. I'm sorry? So when I say that these two are the same vectors, all right? Again, we use these terms. I mean, we're used to using these terms. We're used to saying that a less than or equal to b and b less than or equal to c. A less than or equal to b and b less than or equal to a means a equal to b. But in this context, y equal to x implies that y and x are exactly the same vector, right? They're not distinct. Whereas this is just an operation. You might as well replace this with f of x comma y, f of y comma x, and f of x comma x. Okay. All right. So this is what is a partial order, but this doesn't mean that every pair of vectors need to be comparable. Okay. In addition, if we also have this property that for all x comma y, x is less than or equal to y, or y is less than or equal to x, then this we call this a total order. But for a partial order, just the first three properties are enough. Okay. What we want to show is that these generalized inequalities, they induce a partial order. Okay, and there you'll see why each of those requirements, that it should be closed, convex, pointed, and solid, will come into play. Yes.
So can you explain the example again?
So again, the example is, I define this function, this so-called inequality, which says that vector x is less than or equal to vector y if only the first component is less than or equal to the first component of the other vector. Only the first component. I don't care, I don't even look at the second component. That is why it's possible to choose these arbitrarily and not satisfy antisymmetry. Okay. Any other questions? Okay. So going back, so does generalized inequality induce a partial ordering? So firstly, we want to show that generalized inequalities are reflexive. So consider any vectors, so consider any vector x belonging to whatever the underlying vector space. Okay. When do you say that x is less than or equal to x under the generalized inequality k? When x minus x belongs to k. Correct. So we say that x is less than or equal to y if y minus x belongs to k. But what is x minus x? It's a zero vector. And does the zero vector always belong to k? It does, because it is a cone, right? So x minus x, this is always equal to the zero vector for every x, and this, as since k is a cone, we know that this 0 is always a cone. This is also antisymmetric, which means that x is less than or equal to y and y is less than or equal to x. Suppose that this happens, x is less than or equal to y and y is less than or equal to x. Okay. What does this imply? Y minus x is in the cone. What does this imply? X minus y belongs to the cone. But what is this? This is minus of y minus x belongs to the cone. But can both of these belong to the cone? In general, yes. but we've assumed that the cone is pointed, right? Which means that for a proper cone, it has to be pointed, which means that if you have a non-negative vector, then the additive inverse of that cannot belong to the cone. So here we've used the property that K is a pointed cone. If it were not, then if it were in a general cone, then this is not guaranteed. Right? The third property is transitivity. So suppose that x is less than or equal to y and y is less than or equal to z. This means that y minus x belongs to K and z minus y also belongs to K. Now, can I show that z minus x also belongs to K? And why is that true? What kind of a combination is it? It's a conic combination. We know that K is a convex cone, right? So since K is a convex cone, it is closed under conic combinations. So every conic combination of these two vectors should also be in K. In particular, y minus x plus z minus y, this should belong to the cone, or in other words, z minus x should belong to the cone, which simply means that x is less than or equal to z. Okay, so these generalized inequalities in fact behave like normal inequalities, right? So just like component wise inequalities, for example. I can choose anything I want, right? I just want to show that x is less than or equal to z. For that, I pick this specific conic combination. Any questions? Okay, but these generalized inequalities also satisfy some other properties that we naturally see in inequalities. Right? So one property is, suppose I have x less than or equal to y and let's say u is less than or equal to v. Okay, then this implies that x plus u is less than or equal to y plus v. Okay, again it follows essentially using the same principle. Y minus x should belong to K, v minus u should belong to K, so the sum of those two should also belong to K, conic combination. So x plus u should be less than or equal to y plus v. Straightforward. Okay, but anyway, try it on your own later. It is only for addition. No. Right? It's also true for non-negative scaling. So suppose that x is less than or equal to y, and let's say alpha is something which is greater than or equal to 0, then alpha x is less than or equal to alpha y. Again, this follows just from the property of the cone. So y minus x should belong to the cone, which must mean that alpha times y minus x should also belong to the cone for any alpha greater than or equal to 0, because it's a cone. So alpha x should be less than or equal to alpha y. Okay. But there's something that's a little more interesting. Suppose that xi is less than or equal to yi. I have two sequences, and every element of one sequence is less than or equal to every element of the other sequence. Okay, then it's possible to show that limit I tending to infinity xi is less than or equal to limit I tending to infinity yi. And this basically follows from the property that K is a closed cone. It's closed under limits, because you can look at yi minus xi. If this converges, then it should converge to, if xi and yi both converge, then yi minus xi also converges. And if it converges, it has to converge to a point within the cone. It can't converge to something outside. So this is guaranteed. If K was not a closed cone, then you could not guarantee this. Okay. Okay. I mean, when we take the standard notion of inequality, right? For every set, we have a minimum element and a maximum element, right? But now, as we've seen, not every pair of elements need to be comparable. So if you take the component-wise inequality, then 1, 2 and 2, 1, these two cannot be compared, right? But so we can't really define minimum of a given set. But what we can do is define a minimal element. Okay? So some sets may have a minimum. Okay, some sets may not have a minimum. But every set, as it will turn out, will have minimal elements. So given some set and a proper cone K, then we say that the minimum over all x in S, so the minimum element of x x star is the minimum of S under some generalized inequality that is taken from the cone. If x star is less than or equal to x for all x in S. If it is possible to find some vector which is less than or equal to every vector in your set, then we say that that is a minimum element. but we say that it's a minimal element of S if or the only way that X can be less than or equal to Y is only if Y is equal to X. So in other words, there are no other elements X which are strictly less than Y. Sorry, there are no other elements which are strictly less than Y. Or there are no elements distinct from Y which are less than or equal to Y. Okay, so let's again look at some examples. So consider the component-wise inequality. Yeah.
It's lesser than X, then that element should be X. So it shouldn't be the other.
Which one?
Like if Y is less than equal to X, then Y should be X. Right?
No, so I say that Y is a minimal element. Right? Okay. So let's consider the component-wise inequality in R2. Okay, and let's just take some particular set. Maybe I just choose some rectangular region. This is my set. Okay, so S is the set of all x1, x2. Maybe x1 is between 1 and 2, and x2 is maybe between 1 and 1.5. Okay, so intuitively, what would be the minimum element of S? Yeah, it would be 1 comma 1, right? And that's also something you can prove, right? So basically this point, this would be the minimum. So in fact, this set has a minimum point. Okay, so now let me consider another set. Okay, maybe the following triangular region. This is my S. Does this point have a minimum? Right? It does not have a minimum, but does it have some set of minimal elements? What would be the set of minimal elements? It would basically be this boundary. Okay. This is again just geometric, but you should also try to prove this analytically. Correct? So here's another exercise under the same component-wise inequality. Consider, let's say, a circle, okay, or a circular region. find the set of all minimal elements of this particular set. Does this have a minimum? I mean, think about it. As it turns out, this will not have a unique minimum, but you should be able to find a set of minimal elements. Okay, just think about it later. Any questions? Okay, maybe this is a good point to stop. Again, we discussed a few notions that you've not seen before. These ideas of generalized inequalities from cones. All right. At this point, it's not evident why this is useful. Okay, but I briefly touched upon one kind of application where generalized inequalities may be useful. For example, multi-objective optimization. You have two different objectives which you want to maybe simultaneously minimize, but it may or may not be possible to minimize both of them simultaneously. So if there is a minimum, then that's the best case scenario, but if not, you should at least try to achieve a minimal element. Okay, and in the context of optimization, this is what is called Pareto optimality. Right. So we'll see a little bit of that later on, but generalized inequalities will be used to develop our theory of of constrained convex optimization. We'll see that a little bit later. Okay, but for now, let's stop here.